All right. Uh, Last we left off, right? We had this flow chart right here. And basically, if you want to go to the left side of the flow chart, if you want to be a bit more analytical about things, right, you should ask first what order your differential equation should be in, right? If the answer is going to be first order, which a lot of differential equations are, right? Well, we have a couple of examples or a couple of techniques for us to to start and try to be analytical, find a solution to these things. Of course, when something is first order, that does not guarantee that it is completely solvable, right? Especially some, because of the infinite combinations that we can achieve with different kinds or different classes of functions. Well, something out there is bound to be unsolvable even in the first order, right? But for now, right, we will focus on three out of the five that was introduced to us back then in Kaling 3. So today we'll be learning about variable separable, right, this red one, the linear differential equation, also known as the integrating factor, the orange one, and the exact equation, right, the yellow one. So next video we'll talk about these guys, right? The differential operator, and then the uh, method of undetermined coefficients, and for the last video we'll talk about the Laplace transform itself. So let's start off with our variable separable functions, right? Variable separability is quite self-explanatory, right? If you can somehow manage to get it such that your differential equation can be decomposed or just composed of just one all variables of one variable of one type on one side is equal to all of the variables on the other side of the other type, right? If you can manage to get it like this, congratulations, this is now a variable separable differential equation. And for this, or rather for us to get the solution here, right, we just need to integrate. That's it, right? The thing about this is that if we're going to see, right, our differential equations, most of them will use this fraction notation, something like this or something like this. And basically what we can do from there is do something that physicists would call illegal, right? But what we can do is we can separate those two, right? Those the numerator and then the denominator, right? And what we can do afterwards is just simply integrate both sides, right? We have a dummy variable here dx and a dummy variable here dy, which makes sense because now we have an integration symbol, right? It's really it, right? Very clear, very easy to understand. And so we'll ease into it for this number one, right? For this example, dy over dx is equal to 6x squared times the square root of y. And in this case, I've highlighted very clearly where the y's are and where the x's are. So let's just try our best to separate these things. The thing about variable separable differential equations is that, well, you can only separate them, right, if they are separated through if they are separated through multiplication, which in this case it is, right? This is by multiply, right? By multiplying these together, or by division, right? So in this sense, if for example something like this were to happen, right, this would already be not, right? It's variable separable because no matter how much you try and move around these two terms right here, 6x squared and square root of y, what will happen is that you will never get to stick the dx just only on the x's and the dy's only on the square root of y here, right? What will happen is that they will always be somewhat together because of the addition symbol. That is why this thing is solvable uh, via variable separable, right? So let's just try. What we can do is divide both sides by our square root of y, right? And then multiply both sides by our dx, right? What will happen then, right? We can cancel the y, square root of y here, and we can cancel the dx in here. And basically what we'll get is something like this. dy over square root of y. Let's make this a bit bigger. Yeah. dy over square root of y is equal to 6x squared times dx. And now we can see, oh, okay, very clear. We know what we need to do. We just need to derive both sides, right? And what we're supposed to do here, just so I remember, right? Say for example, the integral is just big f of x, and the integral of g of y dy here is just big G of y. The thing about this now is that you're supposed to add plus c whenever you encounter any indefinite, right? Any indefinite integral, right? But in this case, right, there are two integrals, and on each side you might want to like do this, then do this. Maybe if you lose track, you might do something like this, which is not advisable. That is why we only add the plus c to one side, okay, for us to get the general solution, right? Okay, now let's just try and integrate this, right? What we can do in here, if you are confused, is you can just turn it back into its power representation. Y raised to what? Because your y in here is in the denominator, that will be a negative exponent. And because it is a square root, that will be negative 1/2, right? dy is equal to 6 times x squared dx. And now here we use our power rule. Very clearly, our power rule is just going to be something like this. You want your original, right? And then you add up 1, right, on the exponent, and then you divide everything by that same exponent that you've just edited, is equal to 6 times x. Let me try out that 6 again. There you go. Times x squared plus 1 all over 2 plus 1. And then I will elect to have the plus c in there. Negative 1/2 plus 1 is 1/2. Negative 1/2 plus 1 is 1/2. That means that if you're going to fold this, this becomes a 2, right? There's a 1/2 in the denominator, which makes it, if you flip it, becomes a 2. And then now this whole thing right here is just y raised to 1/2, or just 2 square root y. In this case, now you will also have 6 times x cubed over 3. And cancel, right? You will see that this is just 2. And in fact, what will happen is something like this, right? What we will get is 2 times your square root of y is equal to 2 times x cubed plus c. What you might think is that, okay, what we need to do now is divide both sides by 2. Square root of y is equal to x cubed plus c over 2. But then here's the thing about c. C, it literally controls any constant you are thinking of. Therefore, if c over 2 is just another number, c does not care. It is still going to be c, right? Say for example, you have here for some reason a 5 plus a c. 5 plus some number is just another number. So you can just do something like this. Say for example, we have e raised to c. E raised to some number is just another number. So again, it's just going to be plus c. And honestly, I would accept this kind of answer already, right? This is already kind of good to me. But if you want to go the extra mile, of course, you're very free to square both sides. You will get x cubed. Y is equal to x cubed plus c squared, right? That is our... There you go. That is our answer. Okay. And this is what we call a general solution, by the way. Right? A general solution is one where technically many other solutions or many equations fit this thing. If you replace c with 1, that's also a solution. If you replace it with 2, that's a solution. If you replace it with 3 or 0 or pi or 1 million, in this case, as long as that c is a number, it will fit the bill. So if you want to try it out, of course, you're very free to try it out, right? Try and derive the whole equation and make it such that it is 6x squared times square root of y. You will get the same thing, right? hopefully, right? And if you don't feel very confident about your skills, that's completely fine, right? That's completely fine. Okay. What you can do is, of course, check, right? Check. In this case, say for example, okay, we really are going to check it then. All right. Check. All right. Check. Let's try out dy over dx is equal to 6x squared and then square root of y. Right? Square root of y in here is just x cubed plus c. Okay? And then dy over dx, let's just derive this whole thing. We will have 2 times x cubed plus c. That is because of the chain rule. Hopefully, you guys can brush up on your chain rule skills. This is something squared. So, the derivative is just 2 times something. Now, we have the chain rule. We now have to derive whatever's inside because c is just a constant. Well, that gets canceled out. You will get 6x squared from this x cubed, right? From, oh, sorry, 3x squared plus 3x squared. 3x squared. And then now we have 6x squared. And then your square root of y, we just said, was x cubed plus c. So now we see in here, wait a second, there's a 2. And then a 3x squared, that's 6x squared. And then there's an x cubed plus c on both sides. We can see everything has canceled out. This is indeed correct, right? That is how you check a differential equation. Although, at some point, you just stop checking because, well, you will tell yourself, well, I did everything correctly, right? Therefore, my answer should be, at the very least, right. Okay? And now, we'll stop babying you, right? We won't color code this all the way, but hopefully in this case now you guys can see, now you understand how things can be a bit different now with variable separable, right, in mind. Because I put this in here, you are now going to assume that yes, of course, this is going to be variable separable. The thing is how, right? Because there is a negative sign in here, this is going to be undergoing subtraction. But if you can see, this one literally is just 1. It's a constant, right? It's got nothing to it. So if you want to say this whole thing is of the variable, quote unquote, the variable y, right? Everything in there you can represent as y. So in this case, I will color code this myself. That is the color code. So if we then, right, if we then divide everything by 2y minus 1, and then we multiply everything by dx, again, we arrive at much the same thing. dy all over 2y minus 1 is equal to x dx. And hopefully you guys can see what's going on. We integrate. This one, very easy to answer, right? And hopefully this one as well. If you guys do not see the way forward with this one, then you let your u be equal to your 2y minus 1. That is because your du is equal to 2 times dy. We have here a dy, so what we'll do is just remove that 2 and put it somewhere else, like here, right? Now we will have du over 2 is equal to dy, and then, well, everything stems from there. We will get 1/2. Why is there 1/2? Because of this over 2. And then we will have du over u is equal to, in this case, this one is just x1 plus 1 all over 1 plus 1 again, which will be, right, x squared over 2. And again, what I will do is that I will elect to add the plus c wherever I see the x's. Okay? So in this case, hopefully you guys now remember, I know what's supposed to do, what I'm supposed to do rather. It's just supposed to be ln of u. But in this case, u is equal to 2y minus 1. So I will just say it here is equal to x squared over 2 plus c. And again, we can do a bit of stuff here, right? What we can do is multiply everything by 2. And then what we'll have is ln 2y minus 1 is equal to x squared plus, again, 2c. 2 times a number is still just another number, so it's just c. And then, honestly, I can already take this as my answer, right? If you want to go the whole way, go ahead, right? What can we do to separate or to isolate our y? Well, it's inside of a logarithmic function, so what we should do is raise both sides to e. What will happen is that if you have e raised to ln of something, literally anything, you will spit out whatever was in the original logarithm. So that means that now we will have e raised to ln of, right, 2y minus 1 is equal to e raised to x squared plus c. If you guys remember the, what do you call this? What am I supposed to say? Right? The laws of exponents. There you go. If you're adding exponents together, what you're doing is just simply multiplying these two functions right here, or these two terms right here. And again, we've seen this, right? E raised to c, e raised to another number is just another number. So it can be written down as c e raised to x squared. And then these two things can get canceled. You will get your value of 2y minus 1 is equal to ce raised to x squared. And basically, your y, do we still have space? Yes, we do. Your y is equal to, right? Put this to the other side and then divide both sides by 2. You will have 1/2 times 1 plus ce raised to x squared. That is our answer. So again, this is another general solution. And how can I know? Because of the c, right? This is another general solution, right? And again, you guys can do this yourself, right? If you want to check because you don't feel very confident about your answer, you're very free to do so. Just put the y's in here and then, well, do your own work, right? Do your own work. Okay. Finally, we will have number 3, right? For the variable separable case, right? Y secant x dx minus y. Oops, this is not correct. This should be equal to 0. Y plus 1 times tangent x dy is equal to 0. And at this point, they have what we call here a boundary condition. A boundary condition. What a boundary condition is supposed to do is that it can turn a general solution, basically replacing everything in here with a number works, right? That kind of solution. It turns it into what we call a particular solution. By that, we mean only one thing, right? Only one thing is allowed to happen, right? Only one equation satisfies both the differential equation and then the boundary condition. So something to specify, if anything, right? Something to specify the general solution. So the steps in here are not going to be much different, right? First, we have to get the general solution. So let's go ahead and do that now, and let's try to, shall we say, well, let's try to let's try to color code everything so far, right? I will color all the y's with red, and all the x's will remain white, right? So we'll have y secant x dx. And then maybe it would be much better as well if we just switched everything here to the other side. Because of this negative sign, I'm motivated to think that maybe it should have been on the other side to begin with. And in this case, because your y and your 1 are separated by a plus, that means that they all have to be represented by y, right? Basically represented by the same thing. So tangent x, and then this thing is dy, and we can see, oh, all of them are now separated via, right? All of now are separated via multiplication. So we'll just basically do what we do best, right? We separate these variables, these terms, right? So my goal for this side is to be able to find, right? For this side, what I just want is for the y to be here. So I will divide the y here. And then for this side, what I want to do is turn the tangent down here. So I will divide that by tangent x as well. So this is just y times tangent x. And there's nothing on top. What will happen then is, right, secant x over tangent x dx is equal to, right, y plus 1 over y, and then dy. Okay, that is what's supposed to happen. And now we can see we can integrate. Okay, thing about this first one is that this is already quite difficult if you don't remember your trig identities. More specifically, right, how will you know that secant x and tangent x are kind of like the same, right? Or not the same, but how will you know their equivalences, right? Hopefully, we remember that secant is just equal to the reciprocal of cosine. And hopefully, we also understand or remember that tangent is just the same thing as sine over cosine. Okay, so for this case, what can happen is that I can transform this into 1 over cosine of x. And then in here, I can transform it to 1 over sine over x over cosine of x dx. For this thing, we can literally just take its word for it, right? And just divide. Y divided by y, that is just 1. And then plus 1 over y dy. This thing I can already see the integration, right? This one, not so much, right? And what we have now is a fraction over fraction. So what we can do is we can separate them. But we can do the original one, right? The one on the numerator, 1 over cosine of x. And now for the denominator, what I'm going to have to do is flip it, right? And we will be left with something like this. Right? We can cancel out the cosines, and now in here we can just get y from reverse power rule and ln y. Right? Almost done, right? This is going to be 1 over y times dy, the integral of 1 over y times dy. And this is the only problem we have left, 1 over sine of x dx. Right? This is the same thing as your cosecant x dx is equal to y plus ln y. For the people here who remember, right, the integral of cosecant x dx, congratulations. Good thing you still remember that. However, if you don't remember that, here it is. The solution here is literally to just remember that if you have cosecant x dx, the integral of cosecant x dx will be equal to negative ln of cosecant x plus cotangent x plus c. Right? I will elect to put the plus c's wherever I see the x's, and now that is it. That is it. Y plus ln y. That's it. If you do want to see that it works, right? I suppose we can do a little bit of checking, right? Let's just check this. So we will have a negative, and whenever you are deriving, right, an ln, what you should do is you should put the original downstairs, and then on the upstairs, what you should do is divide or derive both of them. So when you're deriving cosecant, what you get is cosecant cotangent, and then, right, what you will get, negative cosecant cotangent yan, and then this one is also negative cosecant squared x. As you can see, both of them have negative, so it might be better if we just group them out, and then have them be plus. And then you see now there are two negatives. So what we do in here is that we just make them positive. And in this case, wait a second, the top has a common factor of cosecant x. And then what will be left is cotangent x plus cosecant x all over, right? All over cosecant x plus cotangent x. And you wait a second. This is the same thing here. Therefore, you can cancel them. And indeed, the only thing that will be left is a cosecant of x. So that is how we know that, okay, this is indeed correct. And at this point, because it's y plus ln y, I don't think I can get it any more simpler than it is. However, you might say to yourself, okay, done. I'm good with this. This is a general solution, right? What we want, because we are given the, what do you call this? The particular, the boundary condition is that we're supposed to now get the particular solution. In this case, what does y of pi over 4 is equal to 1? What does that mean? Well, it basically means that if your x is equal to your pi over 4, that means that your y is equal to 1. Is that right? Yes, that is correct. So we just literally plug in everything we know. If you guys are still not like aware of the conversion between radians and degrees, well, you should brush up on that. This can also be understood as 45 degrees. So we'll just substitute ln of cosecant pi over 4 and then plus cotangent pi over 4 is equal to y, right? Y plus ln y. So 1 plus, oops, sorry, I forgot the plus c in here. It's equal to y, or 1 plus ln 1. The thing about ln 1, we cancel that. That is 0, right? Our goal in here is to get this value of c. Let's try out cotangent of pi over 4 or cotangent of 45 degrees. Well, we can draw a 45-degree angle triangle in here with 1, 1, square root 2. Okay? Quite simple. And this is our 45 degrees. Right? And so, for cotangent, or let's start off actually with cosecant. Cosecant is just 1 over sine. From SOHCAHTOA, we know that sine is opposite over hypotenuse. That means that now, pi over 4, cosecant pi over 4, cosecant 45 degrees will be hypotenuse over opposite, which in this case is now square root of 2 over 1, or just plain old square root of 2 will work. Next, cotangent is 1 over tangent. So that means tangent is sine over cosine. That means cotangent is cosine over sine. Or TOA, opposite over adjacent. That means that your cotangent is adjacent over opposite. But really doesn't matter. Both of them are just 1, right? So 1 over 1 is just plain old 1 plus c is equal to 1 plus 0. So I should just put this to the other side. We will get that your c is equal to 1 plus ln square root of 2 plus 1. Therefore, our mega final answer is ln of, what is that again? Cosecant x plus cotangent x. And then plus your c, which is ln of square root of 2 plus 1 is equal to y plus ln y. That is everything for variable separable. Right? So next video, we will talk about linear differential equations. Okay? So stay tuned for that.